find me in my office, email me. We possibly could have a conversation over email, but you gotta, class is very specific in what I want to cover. I can't spend lots and lots of time on homework, so that's up to you to get those questions answered outside of class. Okay, so we're talking about rates and division. We said a quotient. So really, it's the operation of division, but really what we're talking about here, this would be better as quotient. Quotient is the result of a division. You get a number when you divide, right? You get a number, and we're talking about what does that mean. And one thing we said that means was relative size of one quantity to another. Okay, so here, a car traveled at a constant speed. It traveled 1,829 feet in 19 seconds. Okay, so you've had some practice in class and in the homework with the bars. So can you set up a bar diagram and follow through a progression of reasoning to come up with how many feet did it travel in each second? So see how you can do. See, this is kind of review now. Hopefully we're getting the hang of this. See how you can do on this. And I've got my list to call on you. So be ready. Everyone got the problem written down? Can I go on to the next slide? Okay, where's Tianjin? Tianjin when? I'm going to learn faces too, so you're not going to be able to hide for long. All right, how about Aaron? Where's Aaron? W. Aaron, is this what you initially did with the bar diagrams?
Yeah.
Good, I'm glad. Okay, and then where'd you go from here?
I split the 19 into 5-second segments.
You broke 19 into 5 segments?
5-second segments. So
5-second segments.
10, 15, and then 19.
Okay, if we wanted to know how far it goes in 1 second, what's maybe a more direct way?
I could have done that. I just didn't know if you wanted us to do 19 slashes through 19.
Okay, so.
But yeah, so 1 was 96.3 rounded to the nearest.
Okay, so I don't understand your statement. 1 was 96.3. So let's go back. What did you do first with the 19 seconds?
How much distance they traveled in 1 second.
Okay, so we.
96.3 feet.
Okay, so stop right there. So this is what I heard you say. You said, let's look at 1 second, right? We're going to look at 1 second. What is 1 second relative to the 19 seconds? Where's Daniel? Daniel Machete.
Yes.
Where are you? So what is 1 second relative to 19 seconds?
I don't know.
Okay. Where is Elena?
Here.
Tell me.
How's 19?
What is 1 second relative to 19 seconds? What is it compared to 19?
Well, there's 19.
19 of them, so it's
119.
119. Okay, where is Chloe?
Okay.
Is this kind of how you started?
Yeah.
All right, so where did you go from here?
And since those two lines are relative to each other,
Okay.
the top line also needs to be divided into 19 equal segments.
Okay. So this is showing 1/19 of 1829. Okay. How many generally did this? How many? Oh, good, excellent. Okay, this is the idea. The first bar is going to be our total distance traveled, the second bar our total time. And so if we want to know how far in 1 second, we're first going to say that 1 second is 1/19th of 19. And therefore the distance traveled in that amount of time is going to be 1/19th of our total distance. All right, and what is that number?
96.3.
96.3. Okay, and so thus division. This is why you divide distance by time. So what is the significance of 1829, this distance traveled in 1 second? What is the significance of that? Yes, sir.
It's the average speed.
Yeah, it's the speed, right? So why do we want to know how far it goes in 1 second? Because that's how we look at speed, per unit time, right? Per unit time. So to get speed, this is where distance divided by time, y distance divided by time is the speed. And you said that value was?
96.3.
Feet per second. As the semester goes on, I'll get better and better at this. Right, we'll get better. Okay, so 96.3. So, if 96 is 96.3 a quotient? Is it a quotient? Yes, it is 1829 divided by 19. So therefore, it must be, we said that quotients are relative size. So I want you to have a conversation with the person next to you. How can that number, 96.3, be thought of as a relative size? Go. How can the number 96.3 be thought of as a relative size? Okay. Rather than stop you and start you up again, then here's a second question. We said also a quotient is can be thought of as measuring one quantity in the units of another quantity. So if this is a quotient, it's also that. So so we'll talk in a second. But now, second question: how can 96.3 be thought of as measuring one quantity in the units of another? Go.
I think
Okay. Let's see how you did. Where's Janae? How'd you do on the first question? How can you think of 96.3 as a relative size?
I'm not really sure how to explain it,
Okay.
but, because it's relative size, like, I really don't know how to explain it.
All right, so let me give you a more specific question. 96.3 is the size of what quantity relative to what other quantity?
It is the size of what's relative to 1 second.
Okay, so size of
One.
1. All right. Okay, where is Austin? What do you think? How is 96.3 a relative size?
Because you have 96.3 and that's feet, and then you can think of the other one as 1 second. So
Okay.
you can make another bar graph. and the top one would be 96.3, and it would be 1 second.
Okay. So you're maybe saying, let's look at that right there. And that right there?
Yeah.
So then how's it a relative, how's 96.3 a relative size? Let's see, where is Gilberto? Gilbert, sorry.
Well, 96.3 corresponds to 1/19th of 1,829 feet, which is 1/19th, which corresponds to 1 second.
Okay.
96.3 corresponds to 1 second.
Okay, sure, that's true. Yep. So it's the size of, go ahead.
Well, I remember we said in the other class, relative size is measured one quantity in terms of another. So
That's kind of the second question. Yeah, that's the second question. So yeah, but they're very similar. They're very similar because it's both the same number, but how are they different? Yes, sir.
With relative size, like say if I want to go 3 seconds,
Uh-huh.
all I have to do is multiply 3 times the 96 point magnitude. It's 96.3. So that's why it's called the relative size, because you don't have to do the bar graphs anymore. All you have to do is multiply whatever seconds you're going back by the figure you have.
So he's saying 3 times 96.3 is going to correspond to what? 3 times 1, right? So these are always in relative size relative to another. It's relative size. It's the size of distance traveled relative to speed. It's how much the distance traveled is, relative to time. It's the distance. 96.3 feet. Let's see. Okay, let's try again. So 96.3 is the amount of distance relative to the amount of time. So 96.3 is the amount of distance traveled relative to the amount of time. So if you go 96.3, if 1 second goes by, you go 96.3 feet. If you go 3 times 90, if 3 seconds go by, you go 3 times 96.3 feet. Okay, so 96.3 is the amount of distance relative to the amount of time. All right, what about as measuring one quantity in the units of another? Christian?
How I interpreted that, because I know last time we were saying that the numerator and the denominator, when we express that way, it's pretty much expressing the numerator in terms of the denominator. So I think that says that for this particular system, 1 second is the same thing as 96.3 feet, and vice versa.
Okay, he's saying 1 second, how about corresponds?
Yeah.
Corresponds to 96.3 feet. So how is it measuring distance in, so it's measuring distance in the units of time, right? How is it doing that?
So you're just going, per 1 second, I travel 96.3 feet.
Uh-huh.
So I'm saying 96.3 feet, I traveled that in 1 second.
Okay. So if we want to measure how far we went, what do we do?
If you want to calculate for the distance, for example, with 3 seconds,
Right.
you have to multiply by 3 seconds because the units of feet per second is in seconds.
Right.
So in order to find the amount of feet, it has to be multiplied by the units that it's measured in, which is seconds.
Yeah, so we've got our unit of 1 second, so however many seconds we go, we're going to go that many, 96.3s, right? However many seconds we go, we're measuring distance in the unit of 1 second, where 1 second corresponds to 96.3 feet. So for all the numbers of seconds, every time we go a second, that's going to correspond to 96.3 feet. So we're measuring our distance in units of seconds, and seconds, and each one of those seconds is a 96.3 feet. Okay. Anybody have a question about this? Ooh, it's hot in here, isn't it? Yikes. Okay. Cool. We won't be here long. Yes?
For like any test or anything, are we going to have to specifically identify the difference between relative size and original?
Yes, you should know that you need to know the difference between the two.
Is there any way like you put it more, I don't know,
They're subtly different. Yes, they're subtly different. So we can practice outside of class if you want to. We can talk about it outside and practice some more. And I encourage that with everybody. Okay. So new situation. Try this one. A little bit different though. So plane travel 4,012 feet in 0.002 seconds. How far would it travel in 1 second? Give that a shot.
Just switched into this plus.
Okay. That's all right.
Okay.
So name 270 and date. Thanks. Okay. Do I have all the homework? Where's Shannon? How'd you get started on this one, Shannon?
I put the second on the bottom.
And what did the length of your bar represent for the seconds bar?
1 second.
She made the bottom bar now 1 second. Okay, what about making it 0.002 seconds? Convenient? Is it okay? What's going to happen? Yeah, so then would have to the length of our bar would take us to what, Mill Avenue or something, right? Okay, so much more convenient to do what Shannon said. Oh, what? Let's see here. I just want the diagram. Okay. Wow. There we go. Sorry. All right, so you made that bottom bar. 1 second. All right, keep going. Shannon, you're on a roll, so take it one more step.
I put like the little tick mark for 0.002.
Okay, like right about here.
Yeah. Whatever.
Like way over here, right?
Yeah. And then I put 4012 on the top.
So 4012. Is that
Not the full value.
so? Where will the 4012 be? Yeah, nice, good. Yeah, so if this time, which is 0.002 of 1 second, is going to correspond to 4012, then that's going to be 0.002 of some unknown distance, right? So again, this distance was 4012? And was it feet? Okay, someone take over from there. Let's see. How did Jonathan W? How'd you do?
Then from there I made the end of the top bar. Okay, so continuing, I did, so the bottom bar is 2 thousandths.
Okay, good. So that's 2 1,000ths of 1 second. Good.
Right, and so then I said that 4012 multiplied by 2 1,000ths would be the distance covered.
So you want to take the 4012 and multiply it by 2 1,000ths.
Oh, sure, no.
That's okay. Keep going.
We divided by the 2 1,000ths.
Okay, so 2 1,000ths means how many little pieces do we have?
500.
Yeah, so that's the same as 1 500th, right? So I heard you say you're going to take the 4012 and do what?
Divided by the 1 500.
Okay, that's it, yeah, and that's right, but it's kind of hard to grasp. So what's an easier way to grasp it? What's your name right here?
Peter,
Peter.
just multiply by 500
And why would you? Can you explain why?
because you don't have a compound fraction, and it just shows you logic of how you got there.
Yeah, that's what I want to hear. The logic relative to the quantities. What's the logic relative to the quantities that you would multiply by 500?
we have 500.002 seconds, so you
Right.
need 500, 4,012 feet.
Well said, right? So there's 500 packets of 0.002 seconds in a second, so we need 500 distance lengths of 4,012. So we do still divide, it's like divided by 1/500th, but we really can't escape really having to need multiplication to conceptualize this. We really, that's not 50.0, that's my cursor. Okay, so, and what is the distance in 1 second?
2,000,006,000.
Oh, I see, I get it. I'm with you. I got it. I know, just didn't think. Okay. And that is, so what quantity is that? Feet? Is it feet or feet per second?
For the top bar, it's just feet.
Okay, for the top bar it's just feet.
But it does equal feet per second.
But it equals, it's both, right? It's both. It's feet, it's feet corresponding to 1 second, and so therefore, it's the speed, feet per second. It's both. Okay,
So,
go ahead.
On a test, if you ask specifically how far do you go in 1 second, should we put 2,006,000 feet per second to divide that 1 second?
So if the question is how far does is it a car still? Yeah, I hope so. Okay, so how far does the plane go in 1 second? Would it be feet or feet per second? That would be feet because it's asking how far, right? That's right. What's the speed of the plane? Feet per second, right? Feet per second. Okay, so you still divide, but in this case, when you're dividing by a fraction of a second, we really need to conceptualize it as multiplication. We really can't escape that. Okay, but you're still dividing distance by time to get speed. Okay, any questions on that?
There's no repeat what you said about conceptualizing and multiplication. Is that always the relative size that you're?
It's because we're dividing by a fraction of a second, so it's very difficult to conceptualize taking a quantity and dividing it up into a fraction of a number of pieces. Does that make sense?
Yeah.
So if we divided it by 30, then we know that we're going to have 30 pieces, and each one is going to have a certain quantity, right? But now we're dividing it by a fraction of a number of pieces, and it's just, you got to think, okay, how many of those are in 1 second? We need that many of those in 4,000. That many 4,012 feet to get the distance in 1 second. But it still is division. It's just we kind of need this in this case, we need that multiplication to understand it. Okay. So this looks familiar, right? So what I can do here is I can change the length of these bars. Okay. Actually, what I'm going to do is I'm going to change the length of the red bar, and the blue bar is going to follow suit. It's going to follow suit. So I'm going to take the red bar to here. So you don't. This is just all all estimating. There's no calculating, punching numbers, but it's kind of more estimation. So I'm going to take the red bar to that point right there. So I'm going to increase this is some quantity. I'm going to increase its amount out to there, and then I want you to predict where you think what the blue bar will increase to. What do you think the blue bar will increase to? Okay, so you can work this with your partner. Find someone to talk with. Just moved it up. Yeah. It's the same. I just moved it up. It's kind of fun, right? It's like a game show, but you don't win any money. Okay, where is, did we already talk to Jonathan? Did I recall on Jonathan? Jonathan W? Yeah, I did. Okay, how about Alexander? So,
F or G.
he says F or G. Okay, and so can you articulate the reasoning that you used to come up with that? So how did you kind of think about that to decide that it was F or G?
Well, the blue bar is like 2.5 times bigger than the red bar.
Okay,
Then if you double, like, it looks like you double the size of the red bar.
okay,
And you also double the size of the blue bar, which would be then like 5 centimeters whatever.
okay. So what I'm hearing you say is, however I magnify this one, it will also magnify this one the same amount.
Yeah.
What kind of reasoning is that we've talked about? Scaling, right? If I scale up one quantity by a certain, then it's like our multiplication, right? If I multiply this by some and scale it up, I gotta multiply this by the same amount. So let's see how we did. Oh, went too far. This is touchy. Oh, gosh. I do not win for dexterity. How'd he do? Okay, actually, the actual magnification factor there, I mean, the reasoning was perfect. It's actually like 2.5. It's actually, we just multiplied that bar by 2.5 times. And so therefore the blue bar was also scaled 2.5 times. So he did it, okay? All right, did anyone think about this differently? So I'll take it back to the old spot. Anybody reason about this differently to get that? Or did you all use scaling factor? Anyone use a different train of reasoning? Okay, figure out a different train of reasoning. Go. Talk to your neighbor. How could you do this differently? Okay, there's some hint for you.
Oh, yeah.
So it's really, I started red at 4, ended at 10, and you started at 12. Okay, what's your name? All right. Shayna wants to tell us her alternate way of thinking about this. Go.
Okay, so well, this is what we originally did, but so we counted the boxes, and we know the blue bar is 3 times the red bar, which is 4.
Okay.
So when you stretch it out to 10, the blue bar actually has to be 3 times the amount, so you know the blue bar has to be at 30.
Okay. Is that different or the same as our previous way of reasoning? Is it different or the same? She said, this bar is always 3 times longer than this one. So when I stretch she said, when I stretch the red one to here, I know that the blue one's going to be 3 times longer than that. Same or different reasoning?
What do you mean, we have the same reasoning, or is it the same?
No, I'm asking if her reasoning was the same as the scaling reasoning we did 2 minutes ago. Lots of people are saying the same. Anyone think different?
Well,
I think it's different because the first form was scaling the red one 2.5 times.
Okay, scaling this 2.5 times.
And scaling the top 2.5 times.
Therefore, scaling the top 2.5 times.
This, the way that she's saying, the way that we said it, is saying that you're taking the relative size, so it's the top bar is 3 times as big as the bottom one.
You just won my heart. What did he say? Relative size. Go ahead. Sorry. Yeah, that way, bro.
So, it's relative size. So, like how she's saying, you know,
Right.
you scale this up, it doesn't matter. It's whatever your final answer, whatever your number of blocks is, the top one has to be 3 times as big.
Right. What is the relative size of the blue bar to the red bar? 3. The relative size. This is 3 relative to this one. Or if we measure the blue bar in the units of the red one, it would be. No, if we measure the blue one in the units of the red, 3. Right. If we measure the blue in the units of the red, it'd be 3. So the relative size of the blue to the red is 3. Therefore, if my red is here, where should the blue be? 3 times out there. Different reason. That's different than scaling factor. That's relative size reasoning. That's relative size reasoning. Do you see how it's different? It's saying that the blue bar is always 3 times the length of the red bar. The blue bar is always 3 times the length of the red bar. Versus, if I multiply one quantity this much, the other quantity gets multiplied the same amount. Different. You see it? Okay, so I'll give you another practice here. This is huge for calculus, okay? So this is not, it may seem like, why are we doing this? But this idea of relative size is so key. And we're going to see it all semester, okay? So now, I'm going to start you here. Doesn't really matter, okay? And I'm going to take the red bar out here. See how you do. Okay, I'm going to take the red bar to there. Where will the blue bar end? Okay, practice both ways. See if you can reason it both ways. Go. Yeah, don't try to count. Instead of trying to count the boxes, do this. Like this. Kind of. Here, I'm going to be cruel here. Oh, mean teacher. Mean teacher. Maybe easier. Okay, let's see how you did. Where's Connor? Connor Sutton. Oh yeah. All right, Connor. So I'll let you pick. So I want you to make a prediction and tell me which kind of reasoning you use for that prediction.
Alright, so the red bar
Okay.
looks like it takes about 5 times as much to get to the point.
So you're saying it would take 5 of these red bars to get there? Okay.
So the blue bar would have to
correspond with that by multiplying by 5.
Okay, you also want to multiply the blue bar by 5. Okay, so what kind of reasoning is that? How about this? Do you know what the choices are? Remember what the two choices are?
Root, scaling, and
Scaling,
I can't remember the other one.
okay, and relative size. So did you do scaling or did you do relative size?
Scaling, I
Because you said this one was multiplied by 5, therefore
think.
scaling, right? And where did you guess that? What letter?
Between G and H.
G and H. The suspense is killing me. That's about the closest I can get, and you nailed it, because it's going to be somewhere between those two. There's a jump right where I put the black mark. Yeah, he nailed it, okay? So he nailed it. So he said the red bar, because it's multiplied by 5, the blue bar will be multiplied by 5, scaling, okay? Where is Sean? Okay, so what's the other kind of reasoning we got?
Well, there's the scaling and then the quantity, like putting the quantity into the other units.
Okay, right, relative size. So can you explain it by relative size here?
So like you could either divide, and it'd probably be easier to divide the red one by the blue one.
Okay.
So suppose that's about a fourth of this size. So the red represents 4, the blue represents 1.
Okay, so I'm going to flip the tables on you. So what is the blue bar relative to the red?
1/4.
1/4. He's saying the relative size of blue to red is 1/4. Therefore, can you keep going? So now I'm going to take the red bar out here.
Oh yeah. So I mean, regardless, it's still going to be the same.
So the blue bar will go to.
Yes. So what's that line out there?
So I'm going to take the red bar to here. Where will the blue bar?
It'll cover a fourth of that distance.
Fourth of that, right? So then the new blue quantity will be a fourth of the new red quantity, relative size. And of course, that takes us to the same place. Okay, questions on scaling and relative size before we kind of change this up a little bit.
Is the difference just how you get to the number? Or how?
Yeah, so right, because when I extend the red bar, the blue bar is only going to go to one place. It's not going to go to two different places, right? It's only going to end up being one quantity, or one value of the quantity in the end. So yeah, it's about different reasoning. It's about two different reasonings. Okay, and so what I can do here is just to get the feel of these are changing together. I can just set it and go, all right? And so then as the red one changes, the blue one will always be. And is that scaling or relative size? Relative size. The relative size of the blue bar will always be 1/4 of the size of the red bar. Okay, so what I'm going to do is I'm going to stop that. And let's make it a little bit small. So it's the same thing I just zoomed out, okay? So what I'm going to do is I'm going to take the blue bar and I'm going to flip it vertically onto the end of the red bar. And this should be familiar. Why is this familiar? No, that's not why it's familiar. Homework, right? The last question in your homework had you do this, right? So watch, ready? Did you see that? I'll do it again. You want to see it? Ready? Here we go. So I'm going to flip the blue bar onto the end of the red bar. Okay? Now, listen carefully to my question. I'm going to set this thing going again so that the red bar increases, and the blue bar will increase also, but it will always stay here at the end of the red bar. So all I'm asking you is, what will you see? I'm going to do the same thing I did before, but now instead of having the blue bar up here, it's now going to be, the bottom of it is going to be fixed to the right end of the red bar. What will you see? So have a conversation. So all I'm asking is what you're going to see on the screen. Don't try to extrapolate where we're going. What will you see on the screen? Okay, where's Nicholas? I'm gonna push play, Nicholas. I'm gonna push play. And I'm gonna do the same things before, but now just the blue bar is at a different spot so that it's the bottom of the blue bar is always on the end of the red bar. What are you gonna see? Just what will the screenshot
It's
say?
gonna look like a right triangle, hypotenuse drawn in, it's gonna go up.
So you're gonna see a right triangle going up to the right. What do you think about that? Is that what you're gonna see? The right triangle? Where's Kevin? Kevin, I'm in this? Yeah.
I just said the red line's gonna go to the right,
Right?
and then like the blue line's gonna stay at the end with it, but it's gonna increase up. So it's gonna be, I guess, a right angle, but just on this side of the screen.
A right angle. And what will be maintained when we do this?
Ratio.
The ratio of?
Relative size.
The relative size is maintained, right? The relative size of blue to red is maintained, so that as the red increases, the blue will increase, maintaining that relative size, right? Question?
Yeah, and what if you were to draw a line from the origin to the...
Oh, you're ahead of me. You're ahead of me. Hold on a sec. Have you seen this before in the sky? What is that? Vapor trail of a plane, right? It's a vapor trail of a plane. When you look at that vapor trail, what does the vapor trail represent about the plane?
It's going up and...
What does the vapor trail represent? Isn't that cool?
It's at.
So you see the vapor trail in the sky. What does it represent about the plane? Go ahead. Nice enough. Oh, who said that? Sorry. Where it's been, right? Two planes. Two planes. And it's the vapor trail is showing where each of those planes has been at some point in time, right? I don't want to be in that plane. Okay? Because where it's been would not be a fun ride. So what I'm going to do is we're going to monitor this point right here with a plane and turn on its vapor. Okay? Please work. Ah, there's my plane. See it? Okay? So we're going to put a plane at the top of the blue bar. Okay? And then we're going to turn on its vapor trail. And we're going to monitor where it's been, right? The vapor trail tells us where the plane has been. Okay? So what are we monitoring there then? We're monitoring what did I do? Oh, I didn't flip it. Okay. So where are we going with this? We're making a graph. She said with enthusiasm. Okay. So let's put some actual quantities on these bars. So let's say the red bar is the volume of water, and we'll call it X. Okay. So the red bar is X. X is volume of water in a bottle in milliliters. So the plane doesn't have anything to do with the quantities. The plane is just this visual about the idea of leaving a trail. Okay, so the water volume in milliliters, and Y is the height of the water in the bottle in centimeters. Okay, so what does that point right there represent? What does that point at the top of the blue bar, what does that represent? Rolling around here. Did I call on Shayna yet?
No.
Shayna, what does that point represent?
The height of the water at how much water is in the bottle.
Okay, so you said the height of the water when that much water is in the bottle. Okay, can you be more specific?
Like, so there's like 5.3 milliliters of water in there.
Okay,
So that means that it's going to be 1.5 to maybe centimeters high.
so something around, and so we know what the relative size is, right? So how could you, don't do it in your head, but how could you find that value? What is that value?
It would be 1/4.
1/4 of 5.3, right? So a point in the coordinate plane represents what? It represents a current value and its corresponding value. It represents two values, right? So in this place, that point represents that there's 5.3 milliliters, but it also shows that there's a quarter of that many centimeters high that the water is. Okay, so then I can change the value, the amount of water in the bottle, and what happens? What does that point represent? Where's Kyle?
Here,
Kyle, what does that point represent?
the new height of the water in the bottle relative to the new amount of volume of water in the bottle.
So the new height relative to the volume, is that what it represents? Because the height relative to the volume is the value 4, right? I'm sorry, 1/4. The height relative to the volume is that number 1/4. Is that what that point represents? 1/4? What does it represent? You must change it.
Yeah.
Go ahead.
It's the height of the water.
Which is?
Bottle, which is 1/4 of the volume in the bottle.
And tell me what those are.
Volume's 8,
Volume's 8.
and the height is 1/4 of 8, which is 2.
That point represents that when the volume of water in the bottle is 8 milliliters, there are 2 centimeters. The height is 2 centimeters. Okay? And so what happens when we set this thing going? And we track every point. So now this is the idea of we are going to track every point with the plane and then leave a trail. Maybe. So now we're going to track every point and leave a trail. We're almost done, I promise. Let me turn the plan on. So when you look at that line, what do you see? What does that line represent? Okay, I heard slope, I heard relative size. Is that what constitutes that line?
Like all possible scalings.
All the possible scalings.
And it represents the relationship between volume of water and the height of the water.
Represents the relationship between the quantities.
The rate at which the bottle is filling.
The rate. It's not what I'm getting at, any of these things. When you look at a graph in general, any graph, what is it? It's the points, right? So it's a set of points. And each one of those points means what? It's going to happen. It's going to happen. There we go. When you look at a line or a curve, it doesn't matter. So your image of it needs to be that it's a set of points. And each one of those points corresponds to 2 quantities taken together. When you have this much of this quantity, you have this much of the other. Each one of those points. So graphs are not wires that you bend and move, and sometimes they're straight, and sometimes they're curved, and sometimes they have asymptotes. Okay? From here on out, whenever you see a graph, try to imagine it as what it is a set of points. Okay, announcements. There's a couple people who tried to get in the pretest yesterday morning. I apologize. It is there now. So take the pretest either today or tomorrow. You got to be in the door before 6:30. It's a required element for everybody. And I will try to get Wednesday's homework up this afternoon. Okay? Are there any more announcements, questions?
Do we have presentations this week?
No recitation this week. Oh, is today Wednesday? Friday, that's what I meant. Friday's. Right. We're off for Labor Day.